Okay, should we start the session? Okay. Hello everyone, I hope you all are doing good. My name is Sambhav. Today we are gonna talk about circles, a very basic 2D shape of mathematics or geometry. So I'm just waiting for others to join. So we'll wait for 2-3 minutes so that everyone can join. Then we are gonna start this session. So in your 10th class, this chapter is all about theory. From this chapter, you can expect a theorem, or even if problem will come, no, so they will be asking you to prove something, and that you can prove using theorems based on this chapter only. So majorly we are going to talk about circle and a line, what is the relationship of that line with respect to the circle. So these things we are going to talk about in this session or in this chapter. So yeah, let others join so that we can start the session. You are already familiar with this shape, no? 2D shape, circles, correct? Very basic 2D shape. Yes, yes. Okay. Please join the session. Yes, yes. Come. Now, okay, let me start the session. First thing, if you are having any doubt related to this chapter, you can ask us in the chat box or in the comment section. Okay, we are gonna solve your doubts. Now, circles, the name of the chapter. What are we going to learn in this chapter? So this is the table of content. First, of course, we are gonna talk about the introduction part. Then position of a line with respect to a circle. As I told you that in this chapter, majorly we are dealing with the relationship between a line and the circle itself. So this we are gonna understand. Then we are gonna see number of tangents from a point. So if you are confused, what is a tangent? So again, it's a line only. So very specific type of line. Now, then we are gonna summarize this much only. Okay, should we start? Now, first thing, we need to remind ourselves what a circle is. Circle is nothing but the collection of dotted shape, no? So I'm just trying to explain you that these are nothing but the collection of too many points. So all these points are at a fixed distance from this fixed point. So now I'm using two things, fixed distance and fixed point. This fixed point, or suppose if I increase the number of points which are at a fixed distance from this fixed point, then it will look something like this. Now you can see complete circle, no? Now fixed points, fixed point is what? This point is what? This is known as the center of the circle. And then constant distance or the fixed distance of these points from the fixed point is known as the radius. Now these two terms you are going to use very heavily when you are going to talk about circles. Now other terms would be chord, you know what a chord is, then diameter, diameter is the longest chord, then arc, what an arc is, then sector and segment. All these terms, you are very much familiar with all these terms from your 9th class, no? But in this class or in this chapter, we are majorly interested in a relationship between the line and the circle. Now, there can be three possible cases when we are talking about, when we are drawing a line in the plane of a circle. So this is a plane, no? And in this plane, I can see a circle. So now in this plane, there are two things, suppose a line and a circle. So there are three possible cases. One, that there can be no common points. They can intersect or they cannot intersect, correct? Now, if they are not intersecting, it means there is no common point between the line and the circle, correct? This is possible. Other case would be two common points. Suppose some line is passing from inside the circle, then they will be having how many points? Common points? Two. Then only one common point. So you can understand it like this, that it is just touching the boundary of the circle, that line. These lines, when in the first case, when they are not intersecting, they are having no common point, then they are having no special name. But whenever we are talking about the intersection of a circle and a line, and in these two possible cases, we are going to call the line differently. If we are having two common points, then it is known as secant. If we are having one common point, one only, then we are going to call it tangent. So now you are again seeing the same term, tangent. Of course, we are going to discuss these cases in details now. Now, the same circle I will be using, but the size will be bigger. As you can see here, no common points. This is a line. We can stretch the line infinitely in either direction. But still, even if we are stretching the line, even if we are extending the line, we are not going to see any common point between this line and this circle. They are never going to meet each other, correct? So there is no point, common point, or there is no point of intersection, correct? The line PQ and this circle have no common points, as in this case we can see. In this case, PQ is known as the non-intersecting line. So PQ is the non-intersecting line. It is not meeting the circle. Now, this is very common, but we are gonna ignore this case because we are not gonna use this case now. Now, second case would be the same line is now like this, somewhat tilted or somewhat rotated. Now you can see this line is going from inside of the circle, or in simple language you can say that this line is meeting this circle at two distinct points, point A and point B, correct? So in this figure there are two common points, A and B. A and B and the line PQ and the circle have, in this case we can call the PQ a secant. So if a line is gonna intersect this circle at two distinct points, then we can call such line as secant of the circle. Okay, now one thing, this is the most common type of intersection of line and this circle when they are, or line is going from inside. So it can be like this, it can be like this also, it can be like this also, anyhow. But if line is meeting the circle at two distinct points, then that will be known as the secant of that circle. Now, one very special type of case is when line is meeting the circle only at one point. Suppose if you are having any circular shape and a line is just touching the circle, then they will be having only one common point, correct, or point of intersection. In this figure you can see line PQ is meeting this circle only at one point, point A. So in this figure there is only one point A which is common to the line PQ and the circle. So in this case we are gonna call this line a tangent to the circle. So whenever a line is gonna meet the circle only at one point, then that line will become the tangent to the circle. It can be anywhere, not only this, but this can be tangent. Suppose this is the meeting point, this can also be tangent, this is the meeting point, this can be tangent, this can be the meeting point, correct? So any line which is only touching the circle at only one point will always be known as the tangent to the circle. Now, majorly in this class we are going to talk about the tangent and this circle. So it means we are dealing with those lines which are going to touch the circle only at one point. So there are some theorems that you can expect in your exam, that examiner can give you in your exam paper. You need to give the proof, okay? Also there are some problems also that you can solve using these theorems also, these theorems only. Now one more thing, see, secant is a line which is intersecting with the circle at 2 points. Tangent is a line which is intersecting with the circle only at a one point, correct? Now let me ask you one thing. Here in this case you can see a tangent, no? At this point of intersection, if I try to tilt or rotate the same line even by the slightest, then what will happen? So let me use white color only. So it will be something like this, or even closer to the previous line. Now I can see this is the first point of intersection. Now I can see one more point, correct? So how many point of intersection now? Two. So can I call this new line a tangent to this circle? No. By definition, we cannot. So there is only one tangent possible at a single point of circle. At a single point on the circle, there is only one tangent possible. If you try to tilt it or rotate it even by inside the circle, okay? So there is only one tangent possible from a single point on this circle. One observation. Now, a tangent is the secant when both the endpoints of the corresponding chords coincide. A tangent is nothing but the secant of a circle. See, secant is having two points of intersection, correct? A tangent is having only one. So here, according to the statement, a tangent is the secant when there's a condition, when both of the endpoints of the corresponding chord coincide. Whenever both the corresponding points of the chords are going to coincide, this is the chord, no? As you can see, suppose this is the secant, these are two endpoints or two meeting points. If they are going to coincide, so they will be somewhere here, correct? If you try to create the same line, so it will be somewhere here. Now you can call it a special case of secant when both the points of the same chords are coinciding at the same. It's a special case. Now, once now, as you can see, I'm gonna use better lines now. So this is the only line that is there passing through point A, which is on the circle and is known as the tangent. If I try to tilt or rotate the line even by the slightest, then it is touching the circle at two distinct points. Again this one also. So this line is touching this circle at this point, this one at this point, this one at this point. So they all are secant. So only one line can be drawn from a single point on the circle, that will be the tangent. Now same we are going to discuss in other way also, don't worry. One more case. Suppose this is the tangent, correct, meeting the circle at only one point A. This tangent can only have one line parallel to it, which is also known as the tangent. So there is only one tangent possible which is parallel to the given tangent. How? So this line you can see, correct? That is P dash Q dash. Suppose this line and this line PQ, they are parallel. But is PQ a tangent? No, it is not. Because PQ is meeting the circle at two distinct points, these two. So it is not a tangent, it's a secant. But if I'm looking at P dash Q dash, it is a tangent and it is parallel to P dash Q dash also. So this is meeting at this circle only at this point. One second, only at this point, point B. Understood? Now, if I try to create more parallel lines, then they will be in between only, or if they are outside, then they are not meeting the circle at all. Suppose this is one more parallel line, so there is no point of intersection, so no need to discuss about them. But if I try to create more parallel lines which are having point of intersection with the circle, then it will be something like this. It is parallel to these two, but they are not tangents. They are also parallel to these two, but they are not tangent. So it means a circle cannot have more than two parallel tangents. So at a single point you can only have one tangent, and to that tangent you will be having only one parallel tangent. Suppose if we are talking about, let me use the image again, one second. Suppose if we are having one tangent here like this, okay, then there is only one more tangent possible which is parallel to this one, and it will be on the opposite side of the circle, this one. You can draw any tangent, it will always be having only one more parallel tangent to this one. Suppose they are meeting like this. So this is the result that you can deduce from this one. Now, secant, tangent and point of contact. So we are majorly using these three terms, no? Secant. Secant, what is a secant again? A line which intersects the circle at two distinct points. Simple as that. If a line is meeting at the circle at two distinct points, then it is known as the secant. Then we are talking about tangent, a line which touches the circle at exactly one point. If a line is touching the circle exactly at one point, then it will be known as tangent. Then third term that we are using very heavily is point of contact. Of course, the point of intersection or the common point between any line and the circle itself, will be known as point of contact, the common point of the tangent and the circle. This will be known as the point of contact. So these terms we are going to use very heavily whenever we are going to talk about a tangent and the circle. For secant, maybe, may not be, we are not going to use this term, but of course tangent and point of contact we are going to use. Now let's talk about one theorem. This theorem can come in your exams. Examiner can ask you the proof of this theorem, and this is also very widely used. Theorem 10.1 says that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So we know all the terms, no? The tangent means that line which is meeting the circle only at one point, correct? Then at any point, so it can be anywhere, the point can be anywhere on this circle. Then circle, of course, the collection of points that is perpendicular. Perpendicular means that tangent and one more line we are talking about here is the radius. If suppose we are joining the point of contact with the center point, then that will be what? The radius, because point of contact is at the boundary of the circle, correct? Then this will be the radius. So now according to the statement of the theorem, this radius and this tangent, they are perpendicular to each other. It means they are making 90-degree angle. We need to prove this. Okay, how can we prove this? First we need to understand one thing, and that is this concept. In between a point and a line, there are multiple ways to join them, correct? Suppose this is a line and this is a point. So I can join them like this, like this, like this, like this, even in zigzag way, in any way possible, I can join them. But one thing I will always realize is the shortest distance from a fixed point. So this is the fixed point, you can name it if you want, to any point on a fixed infinite line. So this is the infinite line, correct? Is the length of the line segment which joins the point to the line and is perpendicular to the line. In simple language, you can say that the shortest distance between any line and a fixed point will always be the perpendicular. Okay, so this will be the perpendicular. This will be less, a greater length than this one. This will be lengthier, this will be lengthier, this will be lengthier. So the shortest distance between a point and a line will always be the perpendicular. This concept we are going to apply in proof of theorem 10.1. Here we are going to apply the same concept. How? Suppose if somehow I will be able to prove that this is the shortest distance, then automatically this line segment is what? This line segment is joining this point and this infinite line, correct? So if this is the shortest distance, so then it means it is perpendicular, correct? So if somehow I will be able to prove that this is the shortest distance, then automatically I will be saying that this is the perpendicular, correct? So this will be the approach that I will be using now. Now, first we need to create a proper diagram now. We need to do some constructions also here. Now, so here in your exam paper, how will you write? First, you are going to write the statement of the theorem. Then you will write what is given or what you are considering. In given part, you can consider things like this: a circle, then name of the center point of the circle. In this case, we are going with O. Usually we go with only. So a circle with center O and a tangent XY to the circle. So this XY is a tangent. So there is only one point of contact or one intersection point here. Suppose this one. Now, according to the statement, we need to join this center and this point of contact. Okay, we are going to join them. Now, at the point P, so this is point P here. We need to prove that OP is the perpendicular to XY. So we need to prove this is P here, that OP is perpendicular to XY. This is what we need to prove, and this is what we are considering. O is the center point, XY is the line, and P is the point of contact. Construction. What type of construction we are doing here? See, One thing is that I'm gonna draw a line segment like this. So Q will be a point on line anywhere, you can consider it to be anywhere. This side doesn't matter. So Q will be a point which is on the line XY. Take a point Q on the line XY other than P. So this is P. So other than P, you can consider any point Q anywhere on this line and join OQ and R be the point where OQ intersect the circle. So now we are doing one thing. We are joining O and Q. If we are joining O and Q, then one thing I can see that this line segment is meeting my circle at some point. Let's name it point R. Okay. Now, if you observe very carefully, OR is what? OR is a line segment which is joining the center and the boundary of the circle. So it means OR is the radius. Same goes for OP. OP is also radius. Now I will give you a rough idea. Look at this. According to Euclid's geometry, a part can never be greater than the whole. Correct? Or in other language, a whole is greater than part always. Now look at this. OQ. OQ is the whole line segment. OR is the part of OQ. So we can say no that OR is part of OQ. So OR can never be greater than OQ. Correct? Now one more thing. In the same circle, I can see two radii, OR and OP. Radii of a same circle are always equal. So if OR is not greater than OQ, how can OP be greater than OQ? Not possible. Correct? So this will be the approach that we are going to take. Now, here, the point Q must lie outside the circle. It will be lying outside the circle only. Why is that? Because there is only one point of contact. So the line is not passing from the inside of the circle. So every other point on this line will always be lying outside the circle. Correct? You can consider that this point Q anywhere. It will always be lying outside the circle because the only point that is point of intersection or point of contact is on the boundary of the circle. That is also not even the inside. That is on the boundary of the circle because this circle is dividing the plane in three parts: the inside, the boundary itself, and the outside. So if the point of contact is at the boundary of the circle, then there is no point with on this line which is lying inside the circle. So every other point other than point of contact will always be outside the circle only. So the point Q must lie outside the circle. Now it follows that OR is lesser than OQ. Fine. Because a part is lesser than the whole always. Correct? If OR is lesser than OQ and also OR and OP are equal, this is P, because they are radii of the same circle, then we can simply say that OP is also lesser than OQ. Correct? OP is lesser than OQ. If OP is lesser than OQ, why we are doing this? Why we are proving that OP is lesser than OQ? Again, we need to prove that OP is the shortest distance between this point and line. Correct? So that's why we are just considering any point which is not P, other than P, any point on this line, and somehow we are realizing that every other point is lying outside the circle. So it will always be at a greater distance from the center other than OP. So OP will be the shortest one. Correct? Now here, since this happens for every point, you can consider any point. Suppose this one, this is Q, so suppose this is X. So if I am joining OX, then there's one more point of contact, right? Suppose this is R dash. So again, same thing you can say for OX, that OX is greater than OP. Why? Because OR dash is equals to OP. OR dash is a part of OX. OR dash is lesser than OX. So it means OP is also lesser than OX. Now let me join one more line. So this is also true for this one. You can do for any line, it will always be lengthier than OP. So OP is the shortest line segment or shortest distance between the center point and this line. Understood? Now, if OP is the shortest of all the distances of the point O to the point of XY, then as we know that the shortest line segment that will be there in between a point and a line will always be perpendicular to that line, correct? So it means that OP is perpendicular to this line segment, this line XY. So this is how you can prove theorem 10.1. This is the proof. You are just using very basic, very simple what should be concept of geometry, that in between a line and a point we can join them in multiple ways, but the shortest distance will always be the perpendicular drawn from the point onto the line, correct? So the same concept we are applying here. Somehow we are proving that OP is the shortest distance. How? You can consider any point which is lying on this line XY. It will always be lying outside this circle. So it means that it will never be lesser than any radius value, correct? So it means that OP is the shortest distance. If OP is shortest, then it will be making 90-degree angle, or it is perpendicular to the given line XY. So this is how you can prove theorem 10.1. Very easy to prove. You can very easily score in this chapter. So for now, let's take 5-minute break. So after this break, we are going to continue our discussion on this chapter circles, and we are going to see one more theorem, theorem 10.2. One problem is there, also one different kind of scenario we are going to talk about. So let's take a break of 5 minutes. After this, we are going to continue our discussion. Okay. Now let's continue our discussion on chapter circles. So till now we have understood what is the relationship between a line and a circle, what type of relationship there can be, how many cases there can be. There are only 3 cases. One, there can be no point of intersection. Then other can be there can be 2 point of intersection. That line is known as the secant to the circle. And the third case is that a line and a circle will be having only 1 point of intersection, or known as point of contact. Then the line will be known as the tangent to the circle. Now we also saw how to prove theorem 10.1, correct? Now let's talk about one more scenario, one different type of scenario. Till now we are talking about a relationship between a line and a circle, correct? But now we are gonna understand the same relationship but from a different point of view. This time We are going to use a point now. A point can be anywhere, correct? As I told you that a circle can divide a plane in three parts: the inside of the circle itself, and the outer of the circle, correct? Or the outside of the circle. Now a point can lie in any of these three. It can be outside, it can be on the circle, or it can be inside a circle. Depending on the position of this point that we are considering, how many tangents there can be. This is the relationship that we are going to discover now. Briefly, I will tell you. If a circle is, if a point is inside the circle, then there will be no tangent. Number of tangents would be 0. If there is a point on the circle, then there is only one tangent possible, which will be passing from that point, as we have seen briefly in one of the slides. No. Then if a point is outside the circle, then there are two tangents possible, which you can create from that point onto the circle itself. Now let's talk about each of these cases one by one. Now, as you can see, this is the circle, and in the first case, we are considering point to be inside the circle. So this is point P. One thing you need to remember, we can only call a line tangent when it is meeting the circle at only one point, correct? If any line is meeting the circle at two distinct points, then that will be known as secant. Suppose if I try to draw a line which is passing through this point, then it will look something like this, correct? Now look at this line and the circle. At how many points they are meeting each other? Two. There are 2 points of intersection, this one and this one, correct? So this point and this point. So can we call it a tangent? No, we cannot call it a tangent. Why? Because for a line to be tangent, it needs to meet the circle only at one point, correct? Here we can see that the line is meeting the circle at two distinct points, so it is not a tangent, it's a secant. Now again, if I try to create one more line, then it will also pass through the circle and it will be meeting the circle at two distinct points. Okay, let's try more. Again, same thing is happening. So whenever a point is inside the circle, we cannot draw any tangent, correct? Now, how many secants are possible? Infinite, because we know from a point, or if we consider a point, there can be infinite lines which are passing through this point. So there can be infinite secants possible, but how many tangents are possible? None, 0. Now there is no tangent to a circle passing through a point lying inside the circle. Whenever we are having any point inside the circle, there will be no tangent at all. Second scenario, second case would be the point is on the circle now. The point is lying on the circle now. Now here one tangent is possible. Let's see. As you can see, this line is meeting this circle at only one point, the given point P, correct? Now this is a tangent because the circle and this line are meeting only exactly, they are only meeting exactly at one point, point P. Suppose if I try to rotate this, or if I try to tilt this line, even the slightest, then it will look, one second, then it will look something like this, no? So again, it is meeting at two distinct point P and this one. Even if you go in between, so it will be meeting the circle at two distinct points. So there is only one tangent possible. So what is written here? There is one and only one tangent possible to a circle passing through a point lying on the circle. Whenever a point is lying on the circle, then there is only one tangent possible. It can be anywhere. Suppose the point is here. So there is only one tangent possible, this one. Other than this, every line will be a secant. Understood? Third scenario, third case is very interesting. If a point is lying outside the circle, so it can lie anywhere, correct? Inside region is very fixed region, correct? Boundary also very fixed. Inside space is the area or this is the circumference, but outside it's infinite plane, no? So it can be anywhere. Now from this point, how many tangents can we draw? We can draw infinite lines passing through this point and which are gonna meet this circle, correct? That is possible. But if we understood the concept of tangent, the line should be meeting the circle only at one point. So how many such lines are possible? Only two. So in case if a circle is given and the point is lying outside the circle, then there are only two tangents possible, like this. Now every other line you can try to create any other line that will be meeting this circle at least 2 points, or it will not meet the circle at all. Now these two tangents that you are seeing here are also equal in length. It means that point of contact to P, or the given point, this length, point of contact to the point P, that length is equal, because of course it's a ray, no, starting from a point but there is no end point. So of course they are not equal, or we don't know for sure, but this segment is equal. This is what we are going to prove also. But for now you need to understand this. If a point is given which is lying outside the circle, then you can draw two tangents from that point. So there are exactly two tangents to a circle through a point lying outside the circle. That is possible. Now based on this, as I told you, there's one theorem. Theorem is theorem 10.2. so let's talk about the statement first. So theorem 10.2 states that the length of a tangent drawn from an external point to a circle are equal. So it means we are only talking about the distance or the length of line from point to point of contact, this much. So it means suppose this is A and this is B, the point of contacts, then PA and PB, they are equal. How to prove this? There are two ways to prove this. First, I will be using the different method, then we are going to talk about the Pythagoras theorem. So Pythagoras theorem will help us here also. So that will be second method. But what is the first method? Let's see. First, we are going to consider a circle. So in your exam paper, you will be writing everything what is given or what you are considering. Given a circle with center O. Okay. A point P lying outside the circle. So this is point P which is lying outside the circle, and two tangents PQ and PR. As we know that from a point lying outside the circle we can draw two tangents. So PQ and PR are our two tangents on the circle from P. So it means we need to prove that PQ and PR are equal. So to prove PQ is equals to PR, this we need to prove. Construction, of course we need to do some construction here also. We need to join OP, OQ and OR. Okay, OP we need to join, we can do that, OQ and OR. So like this, you need to draw dotted line you want, or you want them to be very clean, that also you can do. So in your final exam paper, your figure or whatever image you are creating there is gonna give idea to examiner how well you know about the proof of the theorem. So please try to create a very neat and clean diagram or figure in your answer sheets. Okay, then name them very properly. If you are naming it O, if you are writing the circle is with center O, write O only here. If point lying outside is P, so this should be P. If the point of contacts are Q and R respectively, they should be Q and R respectively. Okay. Now, after joining them, the shape will look something like this. A circle, this OQ and OR, the tangents. So we are joining PO. Are you having any idea how we are going to prove them equal? According to theorem 10.1, the point of contact of the tangent and the radius that we are drawing through point of contact, then those two lines are perpendicular to each other. For any tangent, the point of contact and the line segment joining the center and the point of contact will always be perpendicular to each other, correct? So it means this is perpendicular, same goes for this, perpendicular. Now I can see two triangles now. First one is PQR, the second one is first one is PQO, second one is PR. Both the triangles are right angle triangle, correct? In triangles chapter, we understood the concept of similarity, correct? But in 9th class, we understood the concept of congruence. What is congruence? Congruence is when two figures are having same shape and same size. Exactly same shape, exactly same size. If they are having that, then they are congruent to each other. If two things are congruent to each other, then all their corresponding parts are equal. Whether it can be angles or it can be side lengths, they are equal. If two figures are congruent, then all their corresponding parts are equal to each other. Now, if somehow I can prove that these two triangles are congruent, then we can use CPCT there, and according to CPCT, we can say that PQ is equals to PR. As of now, we don't know if they are equal or not. But if somehow I will be able to prove that these two triangles are congruent, then for sure we can use CPCT and we can state that PQ is equals to PR. Correct? Now, in case of two right angle triangles, we can always go for RHS congruence rule. Correct? What is RHS congruence rule? In any two right angle triangles, if the length of hypotenuse is equals to the length of hypotenuse of other triangle, and also the length of one of the sides are equal, corresponding sides, then the two triangles are congruent, correct? Now here, as we can see that these two triangles are congruent, correct? So by theorem 10.1, of course, these two angles are 90°. So we are going to use, first we need to write it like this, that angle OQP is equals to ORP is equals to 90° by theorem 10.1. If you want, you can write down the statement also, that is also applicable. Now in right triangles OQP and ORP, in these two right triangles, we can see that OQ is equals to OR. OQ and OR are equal. Why is that? Because they are radii of the same circle. In any circle, the length of the radius will never change, no? And OQ is a line segment joining center with a point on the center on the circle. Same goes for OR. OR is a line segment joining the center and one of the point on the circle. So both of them are radius. So they are equal. Now we can also see that OP is equals to OP. Of course, it's the common side. It is equal only. Now OP is also the side which is opposite to the 90° angle in both the triangles, correct? The side that is opposite to 90° angle in a right angle triangle is always known as the hypotenuse. So here in these two triangles, I can see that the hypotenuse are equal of both the triangles and also one of the sides are equal. So we can apply congruence rule, RHS congruence rule. Let me again tell you this statement. According to RHS congruence rule, if in any two right angle triangles, the hypotenuse, the length of the hypotenuse are equal and length of one of the corresponding sides are equal, then the two triangles are congruent. So using RHS, we can simply say that these two triangles are congruent to each other. It means triangle OQP is congruent to triangle ORP by RHS congruence rule. If two triangles are congruent, then we can simply use the CPCT, corresponding parts of congruent triangles. CPCT means that you can simply state two corresponding parts and you can call them equal. Now, we need to prove that OQ is equals to, PQ is equals to PR. They are corresponding sides, so we can simply write PQ is equals to PR. That is using CPCT. It means they are equal. This is what we need to prove. So this is the first method that we are using here. Also, I told you there's one more method, that is the Pythagoras theorem. Pythagoras theorem method is very easy, very easy. Even though this is also not difficult, but still, if you want to go with Pythagoras, then the method goes like this. The theorem can be also proved by using the Pythagoras theorem as follows. We know what is Pythagoras theorem. Square of hypotenuse will always be equals to square or sum of squares of other two sides, correct? So here we know that in this triangle, this is 90 degree, this is 90 degree because of theorem 10.1. So it means OP is the hypotenuse for both the triangles. Now for triangle PQO, in this triangle OP square is equals to sum of squares of other two sides, means OQ square plus PQ square. So OP square is OQ square plus PQ square from triangle OQP. So this you can consider as equation number 1. Then in second triangle PRO, in this triangle OP square, again hypotenuse, is equals to OR square, this, plus PR square, correct? Now as you can see, both the equations are having OP square in the left side, correct? So it means we can equate them because they are values of the same quantity, correct? So we can equate them. So from equation 1 and 2, we can see that OQ square is equals to OQ square plus PQ square is equals to OR square plus PR square. Now OQ square plus PQ square, you can see that OQ square and OR square, they are equal. Why are they equal? Because they are radii of the same circle and we are just squaring the values. So if they are equal, so we can cancel them. Now we are left with PQ square is equals to PR square. So PQ square is equals to PR square. So we can take under root on both sides. So after taking under root, we will be having under root PQ square and equals to under root PR square. Square and root are gonna cancel each other. So what are we left with? PR is equals to PQ. Correct? So again, we are getting the same result using Pythagoras theorem also. This is very easy, but if you want to apply the first method using congruence, that is also easy. Okay. Now you know two methods to prove this theorem 10.2. Correct? So this can come in your exam. Now let's talk about one more problem that did appear in the exam once. So this is a proof also, but we need to understand how to prove this. Prove that the tangents drawn at the ends of a diameter of a circle are parallel. So in one of the slides, I told you that if a tangent is there on a circle, then there is only one line possible which is parallel to that tangent and is also tangent itself, correct? Now here we are gonna prove the same concept, but the main point is that the tangents that we are drawing are on the ends of the opposite end of the same diameter. Now solution would be, first you need to create the figure. So in this figure you are going to consider one circle with center O, correct? So AB is the diameter, that chord which is passing through the center or the longest chord inside a circle. So AB is the diameter. Now the opposite ends are A and B. So passing through this point A, we are having this tangent PQ. Passing through this point B, we are having this tangent RS. There are no other tangents possible which are gonna pass through A and B, correct? These are the only two tangents possible. We need to prove that these two tangents are parallel to each other. How? First, you need to write everything what you are considering. Okay, so let us consider a circle with center O and diameter AB. Let PQ be the tangent at point A and RS be the tangent at point B. Now, we have drawn the very neat and clean figure. We have described what we are considering. Now, continue. We need to prove that PQ is parallel to RS. That is what we need to prove. Proof. Since PQ is tangent at point A, since PQ is a tangent at point A, then from theorem 10.1, the line segment joining the radius, the center of the circle and the point of contact will always be perpendicular to the line that is tangent to the circle. So these are perpendicular, it means 90 degree. So PQ is perpendicular to OA by theorem 10.1. Therefore, OAP is 90 degree. Correct? Same we can apply in case of the other tangent. So RS is the tangent, B is the point of contact. So OB is the line segment joining the center and the point of contact B. So it means OB is the perpendicular. So if OB is the perpendicular, then they are making 90 degree angle. So RS is the tangent at point B. So it follows that RS is perpendicular to OB, theorem 10.1. So it means OBS is 90 degree. So OBS angle is 90 degrees. Now, if you look carefully, look at these two angles. Look at the position. These two angles are at alternate position with respect to this transversal. Correct? Consider this AB to be transversal. Because what is a transversal? A transversal is a line or line segment which meets any two lines or line segments at two distinct points. Correct? So AB is acting as a transversal to these two lines PQ and RS, meeting these two lines at A and B respectively. Now, if I'm looking at this angle and this angle that we just proved that they are 90 degree, then they both the angles are at a position of alternate interior angles. Correct? Now, in a very special case, the value of alternate interior angles are equal. See, let me describe this again. See, there are two lines like this, suppose, and a transversal is acting like this. Even though these two angles are alternate interior angles, but they cannot be equal to each other. Why is that? Because the lines are not parallel. Or the converse. If the value of these angles are not equal, then you can simply state that the lines are not parallel. How about if we are able to prove, let me draw the figure again. If somehow we can see in a new scenario that these two angles, if somehow we can prove that these two angles are equal, then it will follows that these two lines are parallel to each other. So same concept we are going to apply here. Look at the angles. These two angles are at the alternate interior angles position, correct? Now, if their value is equal, so it means that the lines are parallel to each other. So, of course, we did prove them to be equal because this is also 90 degree, this is also 90 degree. Both of them are 90 degree in value. So, of course, they are equal. If the angles at the alternate interior positions are equal, then it means that the lines are parallel. Correct? So this is what we need to prove only. No, for lines PQ and RS with AB as transversal, angle OAP and OBS, these two angles are at alternate angles on alternate interior angles position, and they are equal also. This is only possible in a very special case when the lines are parallel. So both the lines PQ and RS are parallel to each other, or simply you can write it like this: PQ parallel to RS. So this is how you can prove this problem. Now, one thing we realized in this chapter, although there are different theorems, there is too much theory, but nothing is very difficult. Correct? So this chapter is very easily scoreable. So you just need to apply very basic concepts here, and you can score in this chapter very easily, first thing. And if you are confident about this chapter, then you must be feeling confident about others also. So you can divide your focus depending on what type of chapters you are having. From this chapter, most of the time they are gonna ask you a theoretical problem only, where they will be asking you about the proof of any theorem or this type of problem. So there's nothing to worry about from this chapter. You can score easily from this chapter because we are applying only very basic concept. So first, do one thing: try to prove theorem 10.1, try to prove theorem 10.2, and if you understood them, then it will be more than enough. But still, if you want to solve different problems, you can do that also. So this chapter is very much scoreable. Please practice hard, nothing to worry about. Just try to remember the different terminologies that are being used in this chapter. Okay, so as of now we are done with this chapter. So what did we understood? The introduction part, what is a circle, different things related to circles. No, then we understood the position of a line with respect to a circle. Three cases we have seen. Then number of tangents from a point. Three cases for this one also. Now we are done with this chapter. Still, if you are having any doubt related to this chapter, you can ask us in the comment box. So we will be very much happy to help. So we'll see you with one more concept, with one more chapter next time. Till then, bye bye.